Sorry, not sure what happened with that last one. I don't want to re-record the whole video, so I'll just post this as a separate video. Um, so let's get back to what we're talking about. So we have these two coming in towards each other, right? The left box has a plus 30 kilogram meter per second. The right box has negative 30 kilogram meter per second momentum. So the total momentum of the system is actually 0. Seems odd, right? They're both moving. After the collision, they're going to hit and stick. And sure enough, it needs to maintain this momentum. It needs to conserve it, right? What does momentum conserve? Yeah, well, they hit and stuck together. And so object 1 has a mass times a velocity of 0, right? So it has 0 momentum. Object 2 has no momentum. So total, there is no momentum. Is momentum conserved? Absolutely. But was energy conserved, right? Remember, here's kinetic energy's formula. Object 1 had 1/2 mv squared of kinetic energy. So we could look at that, right? It was going 15 meters per second, right? And just doing some back of the napkin math here, right? If I look at 15 squared, I get 225, right? Times the mass of 2 kilograms times 1/2. Right? So we end up with 225 kilogram meters per second. So that's the not kilogram meters per second, kinetic energy, right? So kinetic energy of object 1 initially was 1/2 the mass times the velocity squared. But I can't forget object 2 also has energy of 2 kilograms times 15 squared. Now look, I didn't put a negative sign in, and that's because energy was a scalar. So we end up with 225 joules from object 1, 225 joules from object 2. So we got, what, 450 joules of kinetic energy initially. Then they both come to rest. So the kinetic energy final is 0 joules. There's no velocity for either one, right? So look what happens. There's a change in kinetic energy. In fact, if I do final minus initial, what do I find out? Not that the energy moved to the left. I find out that there was a change in energy that was negative, which means there was a loss of energy. So that collision shows that there's not energy conserved, but momentum was still conserved, right? That's what I want you to get out of it. All right, the last bit of it is, this is an idea called impulse. And so impulse basically just means change in the momentum of a system, right? And another way to think about it is force times time. Right? So that's one way to find impulse, right? Something applies a force over a time period like the wall did in the first scenario, then there's an impulse, okay? So I mentioned this in the beginning, so this is going to kind of sum things up and wrap it up here. Basically, all balls are a little bit, every ball, like a tennis ball, is a little bit squishy, right? So when it hits, it squishes, and it takes time for that collision to occur. So if we know that time, which we have here, and we know that that collision, remember from earlier, we had a change in momentum. We had a final momentum of negative 30 minus the initial momentum. So we had a negative 60 kilogram meter per second change in momentum is equal to the force times the time. And in this case, it's only interacting for what, 0.2 of a second? So if you take that negative 60 over the 0.2 seconds, and that was kilogram meters per second, then we end up with what? 300 newtons, right? So you get 300 newtons, and what does the negative sign mean? Well, it means that the 300 newtons was directed to the left, because force is also a vector. You see that up here, right? So because of that, we know the force that the wall must apply. right? If it was a squishy wall, it probably would have taken a little bit longer time, and time would go up here, but the change in momentum would have been the same. The ball still would have hit at a certain speed and left at a certain speed, and so the force as a result would have been less. And I do need to point something out. This is really important. It's an average force, and I'll show you why that's important. All right. Oh, I'm sorry. Here's the whole scenario. So, ball comes in with positive 30. The collision takes 0.2 seconds. That's the squishy part where it's actually touching the wall, being forced, and it happens very quickly. And then afterwards, the ball leaves with negative 30 kilogram meters per second. Right. So that's where we were getting our values from. That was done earlier in the video, first video. All right. So the last thing, and absolutely the most important thing out of all of this to help you save time on multiple choice for the midterm and the future AP exam and the quiz this week, is how to read these two graphs, right? So if we graphed a graph of the ball as it hits the wall, right? Originally, it was going at 15 meters per second, right? And I'm going to have the collision begin to occur at 0.2. Now, the collision took 0.2 seconds, so it should end by the time we get to 0.4. So that collision, by the time the ball leaves, right, it's going negative 15. That collision takes 0.2 seconds. This is where the collision happens, in the middle part. And then the ball bounces back and just keeps flying backwards at a set speed. So we have the initial speed and the final speed. So we have the initial momentum found here, the final momentum found here, and in the middle is where the collision happened. Well, that's not really helpful to us, that graph, but the graph on the right here is very helpful to us, right? The ball, this is the forces applied to the ball. And we have force sensors on our carts, and you saw this in the investigation that we did. There's no force on the ball, no force on the ball, no force on the ball, and then there is force on the ball, and we said it was negative 300, but that was an average. And so really the force was probably more up at about 600. So this force occurs, peaks at 600, and then the ball squishes and sends it back the other way, right? The wall is applying a force, and it's increasing in force until its maximum amount of compression on the ball. And then the ball starts to rebound and bounce back, and it lets off some of that force until the ball leaves the wall and there's no force on the ball anymore. And this is the part we care about right in here. If the force was constant, right? If it was constant, then we would have saw a peak. Actually, I apologize. It would have been a peak at 300, and it would have just maintained, right? And we would have had a rectangular graph here. The area inside of here equals the change in momentum. That is huge. That is going to save you so much time, because even if that's a triangular area, which we have here, then we can do 1/2 the base times the height and come up with negative 300 newtons.